Hey, Jonathan.
Hey, Professor, I had a quick question regarding the project.
Sure. What's up?
On the finite volumes, is the results supposed to be, I guess, the graph similar to the one that you posted on the project specs?
So it's going to look a little bit different. And so the finite volume one, I think I might have posted, did I post a video of that? But the finite volume one does look a bit different because it handles the the boundary conditions and stuff a bit differently, and so it's not
right.
going to look exactly the same as the finite difference one.
All right. Yeah, it looks like it's actually a better representation, I thought. But I need to double check my code.
No, I agree. I think the finite volume one does do a little better. I did post that video, and so if you go to under project, and then there's two videos. So there's one,
Okay.
There's one called Project 2D Flow FV, and then that's the finite volume one. But
okay.
Yeah, I agree. I think the finite volume one does look a little bit more faithful. Yeah.
Cool. Thank you.
Mm-hmm. We're going to use all three today. And so we're going to do a bit of notes, a bit of MATLAB, just showing you how the finite volume stuff is implemented. And then we'll be doing not really OpenFOAM yet because there's a lot of Linux stuff we have to get out of the way. But yeah, Linux stuff and OpenFOAM. That's a good question, actually. I think, yeah, I'm not sure. Let me see.
The reason I'm asking is because I have like Unreal Engine and I have Magical Voxel and SolidWorks and MATLAB and everything like that on my laptop.
Right.
So I'm scared that like poor laptop is not going to handle it.
Yeah, let me see. Yeah, because it's not installed in like the usual places, and so let's see. Let me see. Open phone. Oops. Shit. Let's see. Download. Let me try open phone system requirements. It's about 1 gigabyte.
Okay, thank you.
Mm-hmm. Let's see. What should you put on your resume? So you can probably just put just Linux, just experience with Linux. All right, it's 5:30, so let's go ahead and get started today. All right, good evening, everyone. How's everyone doing today?
I'm tired, Professor.
Yeah, I think definitely we all are. So yeah, just hang in there just a little bit more. You know, one more week after this week, and then you know, we'll have a summer break after that. Yeah, I'm good. You know, I'm tired too. You know, I think this is kind of just a busy time for everyone. So, you know, looking forward to summer. I think that's my most predominant feeling right now. Okay. And so today we're going to finish up our last set of lecture notes for this class, which is lecture notes 13 on unsteady finite volumes, right? And so we have one more example to go through, and so it's the 2D one. And so, you know, hopefully this example will help those of you out who are working on the project, okay? All right, and then after that, because I don't think this is going to take the whole time, we're going to start our journey into OpenFOAM, right? And so I spent most of today writing up the documentation for it, and so you know, you can find that available on the Canvas site. And so if you go to Files and Lecture Notes, you see I've added a document today called Downloading and Installing OpenFOAM, and it's a bit involved because there's a lot of steps that we have to do in order to do that. Yeah. Right. All right, question. So so how do you save a video file from the MATLAB script? So it creates one automatically. And so if you check within the same folder where you run the MATLAB script from, there should be a file called like project 2D flow or something like that. And so that's the video file that comes out from the script. And so you know, if you kind of search for the for that line inside the code, I think it's you kind of search for the quotation marks project 2D flow, then you can change the name of that file. But the program, the script I sent you already does it for you. Yeah. All right. Ronald, all your projects have me feeling beat. Yeah, you definitely got the worst of it. So all my projects, all my classes that have projects, you're in all those classes, and so it's a lot. Yeah. Okay. So any questions? Are there any questions I can answer before we get started for today? Okay. All right. So let's go ahead and get started. Okay. And where we left off last time was unsteady finite volume problems in 2D. Okay. Okay. And so we spent the majority of last class period kind of deriving this monstrosity of an equation, right? And I kept it, in a slightly different form than what's in the lecture notes, mostly just to, kind of illustrate to you that, this big equation here came from 4 different phase integrals. Okay. And so let me write out the entire thing again, just for completeness, and then we're going to apply this to an example. All right, so first thing we have is we have our unsteady term. Okay, so we have phi sub c at n plus 1, all right? And so that came directly from the time derivative. Next, we have the integral over the east face, right? So it's u delta t divided by 2 delta minus k delta t divided by delta squared. Okay, this is times phi sub big E plus the phi sub c term, so it's u delta t divided by 2 delta plus k delta t divided by delta squared, okay, phi sub c, right? And so all that came from the east face integral, and so I'm keeping all of those in purple, okay? Next, we have the contributions from the north face integral, right? And so this is v delta t divided by 2 delta minus k delta t divided by delta squared times phi sub n plus v delta t divided by 2 delta plus k delta t divided by delta squared phi sub c, right? And so all of that is the contributions from the north face integral, okay? Next, we have the west face integral, okay? So this is plus a minus u delta t divided by 2 delta, okay, minus k delta t divided by delta squared phi sub w, okay, plus minus u delta t divided by 2 delta plus k delta t divided by delta squared phi sub c, okay? And then we have all of the terms for the south face integral, okay? And so for the south face integral, we have a plus minus v delta t divided by 2 delta minus k delta t divided by delta squared phi sub s, okay, plus minus v delta t divided by 2 delta plus k delta t divided by delta squared phi sub c, okay? And so that's everything on the left-hand side, right? And then on the right-hand side, we have a q of xc yc, okay, times delta t plus we have our phi sub c term that came from the time derivative, okay? Right. It's a lot of writing, I know, but you know, I'm keeping in this form just so that you know, we keep all the 4 different integrals separate, right? And of course, you know, since this is implicit Euler, we're going to put an n+1 on everything on the left-hand side, right? Right. And then on the right-hand side phi term, we're going to put a time index of n. Okay. All right. And so if you have an interior cell where you have a neighbor on, you know, all 4 sides here, the north, east, south, and west, then you can apply this this equation directly and just plug in for all this stuff. Okay. But if you have a boundary condition, remember the way that we deal with boundary conditions is that we simply just replace one of these integral expressions with that boundary integral, okay? All right, and so I'm gonna do an example on the next page where I'm gonna work out some of these by hand, and then I'll show you the MATLAB implementation of this guy, okay? All right, so any questions on this? Okay, so let's go ahead and do an example. Okay, so in this example, let's scroll down real quick. And question, so if you have a corner, do you apply both boundary conditions? Correct, yes. And so if you have a corner cell, then you have to apply both of them at the same time. And so you're going to replace two of those colored expressions. All right, so this example, let's say that we have the following equation. Okay. And so let's say that we have partial phi, partial t plus plus 50 cosine of pi t, okay, times partial phi partial x plus sine of pi t times partial phi partial y, right? And so those are our convection terms. This is equal to 3 times partial squared phi partial x squared plus partial squared phi partial y squared, right, plus 3xy, okay. All right, so here's our equation, and so let's go ahead and label, you know, our parameters from here, right? And so right away, we see that, you know, we have this in front of the partial phi partial x, and so this is going to be our u, right? We have sine of pi t, this is going to be our v, and so those are our convection velocities. We have our diffusion constant here, which is our k, and so that's going to be 3 in this case. Okay. And then our source term is this guy on the right-hand side, which is going to be 3 of xy. Okay. All right, and so we know exactly what we need to plug into our equations. Okay. And so for this problem, what I want you to do is I want you to solve this problem using finite volumes for the space discretization and implicit Euler for the time advancement. And just for the sake of our hand calculations, we're going to do it on a pretty simplified mesh. And so we're going to do it on something that looks like this. All right. And so this mesh here is only going to have 16 cells. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, okay? And then for this problem, let's say that we have Dirichlet boundary conditions all around. So we have phi here is equal to 25, phi is equal to 25, right? We have phi is equal to 50, and phi is equal to 50, okay? Right? And so in this example, there's no Neumann boundary conditions. So we just have Dirichlet boundary conditions all around, okay? All right. And so with this kind of grid spacing, or this number of cells, we have our grid spacing delta is going to be 0.25. Okay. And then our time step size for this case is going to be 0.1 seconds. Okay. Just to kind of make our calculations a bit easier. Okay. All right. And so I'm going to go ahead and solve this or find out the equations for, let's do 3 of the cells. And so let's do cell 4, or let's start with cell 6, sorry. So we'll do cell 6, which is an interior cell, right? Let's do cell 5, right? And then let's do cell number 4, okay? Just so that you have a chance to look at 3 different cases here, right? So we have an interior cell, one case with only one boundary condition, and one of the corner cells, so we have to apply 2 boundary conditions there. Okay. So any questions on the problem setup here? Okay. All right. So let's go ahead and get started. So let's start with cell number 6. Okay. Cell 6 here is an interior cell because that has neighbors all around. And so since it's an interior cell, we can just go ahead and plug straight into our monstrosity of an equation that we have on the first page. Okay. And so we look back 2 pages, right? And since we have our interior cell and we have all neighbors all around, we can just plug straight into here. Okay, so plug in for K, plug in for delta, plug in for delta T, plug in for the convection velocities, and we'll get an expression from that. Okay, and because it's an interior cell, all of these terms here that I'm going to circle in yellow. All of these have this. All of these are coefficients for phi sub c. Okay, and so after you plug in for all of the parameters, all of these terms will combine to just a single coefficient. Okay, and so let's go ahead and do that. Okay. All right, and so you plug in for all this stuff, and then I'll spare you the gory details of plugging in and doing arithmetic, but you end up with the following equation. Okay. All right, and so let's see. I can't even read my own writing. So let's see, this is going to be 10 cosine of pi t minus 4.8. Right? And so here our coefficients are depending on time because our velocity is changing with time, okay? And so, when you have those functions, make sure that you account for that in here, okay? And this will be cosine of pi t n. And so, implementing this in MATLAB, you'll see that we'll just incorporate the time directly when we compute the x velocity. Okay? And all this will be for the east neighbor for cell 6. Okay? And so the east neighbor is cell 7. Okay? So that's the coefficient for phi 7. Okay? Next, we're going to have the coefficient for phi 10, which I think is the north neighbor. Okay? And so the north neighbor is going to be 0.2 sine of pi t n minus 4.8 phi 10 n plus 1, okay, plus minus 10 cosine of pi t n. Right, and so this is the coefficient for the west neighbor, which is phi 5, right? Minus 4.8 phi 5 n plus 1, okay, plus minus 0.2 sine of pi t n minus 4.8. Then we have the south neighbor for cell 6, which is cell number 2, okay, right? And then we have the coefficient for phi sub c. And so for phi sub c, we have 20.2 phi 6 n plus 1. Okay? And so that's the entire left-hand side of the equation. And then for the right-hand side, what we have is 0.3 xc yc, okay? And so this term right here came from our source term multiplied by delta t, okay? Plus phi 6 to the n. Okay. All right. And so that is our equation, okay? And so you can see here we have our coefficients for each of the neighbor terms as well as phi sub 6. And then we have the right-hand side, you know, as it is, okay? So for interior cells, you know, there's no stressing with it. You just drop everything into the equation and you're good to go, okay? All right, so any questions on this? Okay. All right, and so that's cell 6. And so now let's work on some of the boundary cells. Okay, so let's start with cell 5. Okay. And so cell 5 is one of the cells that are on the boundary. And so we need to replace one of the face integrals with a boundary condition. And in the case for cell 5, the boundary that that we need to replace, or the face integral, is the west one. Okay. All right. So what color did I use for west? I think it was green, but let me check and make sure. Okay, so for the west integral, I use green. So let me change to green here, okay? And so instead of this integral term or these terms right here, you know, we're going to go ahead and just wipe them out for now and then replace them with the boundary condition, okay? All right. And so in this case for cell 5, we have a Dirichlet boundary condition, okay? And so to account for that, you know, we have the following. Okay? So our integral is usually something like this. And so we have phi v dot n, okay, minus k gradient to phi dot n ds, okay? And so the form that this integral takes with the Dirichlet boundary condition is the following. Right? And so with the Dirichlet boundary condition, this becomes minus phi naught times u minus k times phi sub c minus phi sub phi naught, okay, divided by delta x divided by 2. Okay. Yep. All right. And remember this, we have a minus sign out in front because for the west face, the normal vector is -1, 0, right? And so that's why we have that negative out in front, okay? And all of this is multiplied by delta. All right. And so let's go ahead and simplify this, right? And so we can simplify this by just, you know, plugging things through, okay? And so we multiply everything by delta. We end up with the following, right? So we have a minus u delta phi naught, okay, minus 2k phi sub c, okay, plus 2k phi naught, okay. And we can go ahead and plug in for this stuff, great, because we know for the west boundary condition, phi naught is equal to 50, right? And so you know, and we know delta is equal to 0.25, and I think that's all we need, right? And so we plug those in. And we plug in for u and for k and all that stuff, right? So we know u here is 50 cosine of 50 cosine pi 50 cosine pi t, right? And so we have 50 times 0.5 right? So this is 50 divided by 4. Okay. Times another 50. Okay. Times cosine of pi tn. Right. Minus 2 times k, which is 6. Phi sub c. And so phi sub c in this case is phi 5. Right. Plus 2 times k times phi naught. And so that's 2 times 3, which is 6, times phi naught, which is 50. So this is going to be 300. Okay. Right. Good. And so now that we have this, this expression here, we can go ahead and replace the west terms in general expression with this. Okay. And so all the green terms in our general expression back here, we replace that with, what we just computed. And so all this stuff here, we don't use it anymore, but now we replace this with, what we just computed. Okay. And then we just evaluate things the same way as before. Okay. Okay. And of course, anything that doesn't have a phi, and so in this case, this guy, and then this 300, we're going to move those to the right-hand side because those are no. Okay, so any questions on this? All right. Okay, and so let's go ahead and plug all that stuff in. Okay. And so if we plug all that stuff in, then we are left with the following. Okay. And so plugging in, what we're left with is 10 cosine of pi tn minus 4.8 times phi 6 n plus 1. Right. And so that's the east neighbor. Next, we have the north neighbor. And so the north neighbor is going to be 0.2 sine of pi tn minus 4.8 times phi 9 n plus 1. Okay. Plus south neighbor. Okay, so south neighbor is pi minus 0.2 sine pi tn minus 4.8 times phi 1 n plus 1, right? Then we have the modified phi 5 term, and so this is modified because we we replace the integral. Okay. Okay. And then we have everything on the right hand side. And so right hand side we have a 0.3 xc yc, okay, plus phi 5 to the n, right? And so all that is standard stuff. And then to this we're going to add our terms that we got from the previous page. Okay. All right. And so just take note that these are a little bit modified because we had to, actually, in the previous page here, we hadn't accounted for, the time step size and the, and all that stuff. And so, when you plug this in, just remember that, before you actually plug this in, you have to multiply this by delta t divided by delta squared. Okay. Because these guys here come from the time derivative term. Okay. Because what we just evaluated here was just kind of the face integral by itself, but in order to combine it together with our general equation, we had to combine it together with the with the time derivative, right? Because normally what we have here is we have partial phi partial t, okay? and then we integrate this. This becomes phi sub c n plus 1 minus phi sub c n divided by delta t times delta squared, right? And so we have this extra delta t times delta squared over delta t that comes out from that term, okay? And so the terms that I'm going to write here are a little bit different than the one I had on the previous page, mostly just because, you know, we had to account for these terms, okay? All right, and so let's go ahead and write those down. And so first we have a 1,000 cosine of pi t, okay? And this term right here, this is the term that became of the u delta t phi naught divided by delta. Right. Right. Question. So when the code runs, t is being incremented by the time step 0.1, 0.2, 0.3. Yes, that's correct. Yeah. So each time step, you know, the tn is counting up, and so it starts at 0, then it goes to 0.1, then 0.2, and 0.3. Yeah. So each time that you solve it, it increments up by 1 time step. Yeah. Okay. And then we have a plus 480. Okay. And this term right here came from our 2k phi naught delta t divided by delta squared. Okay. All right. So slightly different than the ones we had here, but that's because, you know, one thing that was missing here was a delta t divided by delta squared. Okay. And so if you apply that delta t over delta squared, then you should get the numbers that I have here on this page. Okay, so any questions on this? All right. Okay, so that's cell 5, and so cell 5 only had one boundary condition, and so now let's do cell number 4, which has 2 of those boundary conditions. All right, and so in this case, we're gonna replace 2 of these integrals. Okay, so let's start with the south one. Okay, so I think I used blue for this, but let me just go back and see. Right. So first, let's look at cell 4. Right, and so cell 4 here is in the bottom right of the domain, and so we have a Dirichlet boundary condition on the south side and one on the east. Okay? And so we're going to replace those integrals. Okay? And so the integrals we're going to place here are the south one, which is this one I have circled in blue, okay, and also the east one, which is the one I have circled in purple here. Okay? All right, so let's start with the south one first. Okay. All right, and so instead of all those terms that I've circled there, what we're going to have instead is integral on the south face of phi v dot n minus k gradient of phi dot n, okay, ds. Right? And so what we're going to have instead is a minus phi naught v minus k phi sub c minus phi naught divided by delta divided by 2, okay, times delta, right? And I'm not going to make the same mistake last time, and so you know, we're also going to multiply this by delta t divided by delta squared, okay? Because that's the extra factor that we get from you know, from the unsteady term, okay? All right, and so let's go ahead and go and work this out, okay? And so if we multiply that through, then what we get is a v phi naught delta t divided by delta, right? Then we have a minus 2k phi sub c delta t divided by delta squared plus 2k phi naught delta t divided by delta squared. Right? Let me just double check that. 2k. Yeah. Yeah. Okay. All right. And so let's go ahead and plug in for all this stuff. Okay. And we know v is equal to sine of pi t n. Right. K is equal to 3. Delta t is equal to 0.1. And delta is equal to 0.25. Right. And so we plug all that in, and what we get is minus, phi naught in this case is equal to 25, right? Because that's our Dirichlet boundary condition on the bottom side of our domain, right? And so we plug all that in. Let me grab my calculator. Okay. And so we have a 25 times 0.1 divided by 0.25, okay? And so this is going to be a 10 sine of pi t n, all right? Minus 2 times k, so 2 times 3 times 0.1 divided by 0.25 squared. This is a minus 9.6 phi sub c, where in this case phi sub c is just phi 4, okay? And plus 1, right? Plus 2 times 3 times 25 times 0.1 divided by delta squared. And this is going to be a plus 240. And so when you're applying, the south face integral for this cell, you're going to apply this term instead, okay? And so instead of, let me go back. Instead of all these terms here in the blue, we're not going to put this anymore. Now we're going to replace it with, what we just computed just here. Okay. All right. So any questions on this? Okay. All right, and so that's the south integral. So now let's go ahead and replace the east one. Okay. And so the east integral for cell 4 is going to be integral of phi v dot n minus k gradient of phi dot n ds, okay? And we do this for a Dirichlet boundary condition, and we end up with u phi naught minus k phi naught minus phi c divided by delta divided by 2, okay? Times delta t divided by delta squared, okay? All right, and so let's go ahead and plug stuff in for this, or let's simplify this a bit first, right? And so we simplify this a bit, and we get a u phi naught times delta t divided by delta, right? Then we have a minus 2k phi naught times delta t divided by delta squared plus 2k phi sub c delta t divided by delta squared. Okay. All right, and so now we can plug in. Okay, And so here we know that U is 50 cosine of pi Tn, right? K is equal to 3. Delta T is equal to 0.1. Delta is equal to 0.25, right? And phi naught is equal to 25, right? And so we plug all those things in, and what we get is a, let's see, 500 cosine pi Tn, right? Then we get a minus 240, then a plus, should be the same, should be 9.6 phi 4 n plus 1. Okay. Right? And so now we're going to plug this in for the East integral expressions. All right. So a lot of writing, a lot of math, but you know, I'm choosing to do this kind of slowly and systematically, just so that you kind of see, you know, every single step in the process. All right. Any questions before we put this together? First term is cosine. Oh yes, first term is cosine. Yes. Yes, it should be 500 cosine pi Tn. Okay. All right, and so let's go ahead and put all this together, and then we're going to end up with our, you know, with our final expression. All right, and so combining these two boundary integrals together with, you know, the north and the west integrals that stay the same, we end up with the following. Okay, so after plugging in / replacing, what we end up with is 0.2 sine of pi Tn minus 4.8 times phi 8 n plus 1. Okay, so that's the north neighbor. Then we have the west neighbor, and so we have a minus 10 cosine of pi Tn minus 4.8 times phi 3 n plus 1, right? Then we have the phi 4 term, and so this is going to be a plus 29.8 phi 4 n plus 1, okay? This is equal to 0.3 xc yc for our source term, okay? Plus phi 4 to the n, right? And so that came from our unsteady term, right? And then we have all of our boundary condition terms that we just computed. So we have a minus 500 cosine of pi Tn, right? So that came from the east integral, plus 240, plus 10 sine of pi Tn. That came from the south integral, okay? Plus 240. Right? And of course, you know, you can combine things on the right hand side, like the two 240s. You can combine those together. Okay. All right. So any questions on this before we start looking at the MATLAB code? All right. And so let's see how this is implemented in MATLAB. Just so you can see all this in action. Okay. All right. So here we are on the desktop. Okay. All right. And so this is a code that I have uploaded for you. And so if you go to you know, our course website here on Canvas, and you go to week 15, here is the code for it. So Unsteady FVM 2D implicit example. Okay. And you can download the code for this and view it you know, on your computer. All right, And so here we have the code. And so, you know, it's structured in very much the same way as all of our codes, including the final project. And so section 1 here, we define all of our parameters, right? And so we have the length of the domain, we have the number of cells in the X and the Y direction, the grid spacing, we have the diffusion coefficient, which is K, the time step size, and the number of time steps. Okay. Since this is changing with time, I'm going to save a video for this. Okay. And so here's the code to save the video. So very similar to your projects. Okay. And I initialize the time variable. Okay. All right. And so if you're doing the project with finite volumes, this code will look very similar to what you're doing, right? Especially for the base case where you're running just kind of basic schemes. Okay. All right. So first thing we'll look at is line 34, right? And so you can see here we're entering the time loop, and so you can see here we're looping over all of our time variables. Next, we're going to compute our convection velocities. And so in this case, our convection velocities, they're going to vary with time. And so the U velocity is going to be 50 times cosine pi t, and the Y velocity is going to be sine of pi t. Okay, so actually, let me put this, put this on the side so you can kind of view it at the same time. Okay. Right, so here is our example problems. You can see U here is 50 cosine pi t, and V is sine of pi t, right? Then we initialize our matrices, and then we go in and we start working on the coefficients, okay? All right, and so you can see here I have a nested for loop, and so this goes 4i is equal to 1 to nx, and 4j is equal to 1 to ny, and so this will allow us to visit every single cell, okay? Just like we usually do, we're going to compute the ID numbers for all of our neighbors, right? And so we have the ID number for myself, the West ID, the East ID, North and South. And so all of this is pretty standard to what we've been using, okay? And then from here, you start evaluating the integrals, okay? Right, and so you can see here, I've fragmented this into all the different integrals here. So we have East, South, West, and North, okay? All right, so let's look at the East integral, right? And so you can see here, we have two different cases. And so we have one case where we're at the boundary, okay? And so if I is equal to nx, this tells us that we're at the boundary, okay? And then from here, if we're at the boundary, then we have to apply our boundary conditions, okay? And so if we're applying our boundary conditions, you can see from here that we have two different terms, right? And so we have one term that goes on to phi sub c. And so phi sub c here, that's going to be at a at my ID, right? And so the coefficient that we're applying there is a 2k times delta t divided by delta x squared, okay? Actually, I think there's a better example of it down here. Yes, right. Okay, and so, this is just kind of a general. And so if you have a Dirichlet boundary condition, the phi sub c coefficient is 2k times delta t over delta x squared, okay? And so that's what we have here for a my ID, all right? And then for the right-hand side, here we apply our boundary condition, okay? And so for the boundary condition, we have phi naught, which is 25, okay, times a minus u delta t over delta, right, plus a 2k delta t over delta squared, okay? And so you can see here that all of this is added to the right-hand side vector b, as is shown here on the from the lecture notes, okay? Question, so why isn't a minus 2k, right? Let's see, minus 2k. It's not a minus 2k because, for the East integral here, we have this minus and this minus here cancel out. Yes. And so this cancels out here. And then when we move this, when we move this term, because normally, we have a minus 2k delta t delta squared phi naught, but we're moving this, remember, we're moving this over to the right-hand side. And so, since we're moving this to the right, the signs for all these coefficients are going to flip. And so instead of a minus 2k delta t over delta squared, we have a positive 2k delta t over delta squared. Instead of a positive u delta t over delta, we have a minus u delta t over delta. Yep. Mm-hmm. Yep. Question, so does MATLAB not recognize the negative if you put minus u? It does. I think I was just had a brain fart there. And so, yeah, that's a lot easier to read then a -1 times u. Yep. Sometimes I overcompensate, and I think MATLAB will do weird stuff, but in reality, it doesn't. Okay, and so that's for the boundary integral. And so now let's look at the, if we have an interior, okay? And so that's, remember, we only apply this if we're at the boundary, right? And so this I is equal to nx. Otherwise, we have an east neighbor. And so we're going to put coefficients for A d, okay? Which is this, right? And so this is if you refer back to the purple terms back in our general equation, you can see we have these coefficients. And so the coefficients for A d are going to be u delta t divided by 2 delta x plus k delta t over delta squared, okay? Right? And so these two guys are the same, right? And then we have the coefficients for phi sub e, which is this guy right here, okay? And so for phi sub e, we're doing the coefficients for A d e side e, okay? A d e side e, right? And so we have, this guy right here, right? So we have u delta t over 2 delta x minus k delta t over delta x squared, right? Yeah, seriously, yeah. Put everything in parentheses because you never know when the computer's going to do something weird, right? All right, and so that's the east integral, and so all the other integrals are more or less the same thing, okay? And so you're gonna have two cases, one for the boundary case and one for the interior case, right? And so if you refer back to our general equation, the one with kind of the Skittles, taste the rainbow kind of colors, right? You should be able to see that, all of this stuff applies directly to that. The only derivation that you might have to do is for the boundary terms, right? So make sure you're careful with that, okay? But besides that, all of it's still the same, okay? And then besides that, we have to add our source term, which is what we do here, right? And so we have 3 times x pos times y pos times dt plus sol cur at maya d, right? And so that takes care of these terms right here, okay? Right, and so that's directly implemented here, right? And so once that's done, we can go ahead and solve it. And so we invert the matrix, we update the solution, and then we plot it, right? All right. So, any questions on the MATLAB implementation here? Whenever I say Skittles, I think of Taste the Rainbow. I like Skittles though. Skittles is definitely a top tier candy for me. Yeah. S tier. Right up there with Sour Patch Watermelons. I think Sour Patch Watermelons is my all-time favorite candy, but Skittles is right up there too. Okay, so let's go ahead and run the code. Okay, and because our velocities here are changing with time, you'll see that this this solution here will also change with time, right? Right. So my computer's kind of spazzing out a little bit because I'm running Ubuntu at the same time, but you can see here we have our kind of like our membrane kind of bass drop beats thing, like kind of thing, right? Except really slowly. It's like right? Okay, all right. And so I think we did this example before. So I think this was our implicit example when we were doing unsteady finite differences. And so this is kind of just the same thing with finite volumes. Okay, and so the implementation, for finite volumes, obviously is very different than finite differences. But if you tackle it integral by integral here. And I know it's a lot of terms to keep track of, but I think it's better to kind of keep it like this. Otherwise, it gets a little bit too difficult to apply the boundary conditions. Right? Okay, and so that's unsteady finite volume problem. So any questions on this before we move on to OpenFOAM? Okay. All right, and so you guys are a little bit luckier this year because last year this is where the class stopped, and so because of the pandemic and because we took like a week and a half off because of that, I only got basically like 14 and a half weeks worth of content, and so you guys are a bit lucky. So we have about a week and a half left to do some extra stuff, and so we're going to do some OpenFOAM, okay, and so that's going to be new. All right, and so let's go ahead and close this. Actually, I'll leave it open just in case, right? And so now we're going to move on to OpenFOAM stuff, right? And so I spent all afternoon today writing up this documentation, right? And so if you go to the Canvas site and you click on this link right here for downloading and installing OpenFOAM, you can download this very nice PDF that has a lot of pictures and stuff like that, right? And so we're gonna walk our way through this. And so a lot of today is going to be just kind of a tutorial on, how Linux works, and then we'll build on that. And next week we'll start to do, a lot of really nice test cases in OpenFOAM, right? Okay. All right. And so if you open up this document, the first thing that it tells you to do is you need to download and install Ubuntu for Windows, right? And so, I will note that, this tutorial is designed for Windows 10, right? Mostly because I have a Windows 10 system, okay? And so if you have a different version of Windows, or if you have a Mac, your instructions are a bit different. I think if you have Windows 7 or Windows 8, I think Kyle posted the PDF that he mentioned before. I think you can get it working with that, because I think I just took a brief look, but I think it uses Cygwin. And so Cygwin is another program which you can use to run Linux stuff in Windows. And I think that works for Windows 7 and 8. But this one I'm using the Windows 10 version, because it's I never learned Cygwin, and Cygwin was a different kind of thing for me. Right? All right, and so step one here is to just download and install Windows Subsystem for Linux and Ubuntu. And so this was the email that I sent out earlier this week, right? And so if you read that email and you installed the stuff, then you should be good to go, right? And so if you haven't done that, you need to do that. And part of those instructions means that you have to restart your computer, okay? And so I won't go through this here, because the document, goes through pretty step by step. And so I tell you exactly where to click every single time, okay? And so I won't go through that, okay? And so I'm going to start with step 2, which is to launch Ubuntu, right? And so if you've installed the Windows Subsystem for Linux and you have Ubuntu installed, you can just launch it straight from your start menu, okay? And so you can go from here, and then you can scroll all the way down to U for Ubuntu, okay? Forgot my alphabet, right? And then you should have something that appears just like this, okay? And so it's going to look pretty empty at first, right? And so because at first, Ubuntu is just it's basically just a Linux shell, right? And so what that basically means is that it allows you to modify and run Linux stuff through a text terminal, okay? And I think that's going to be pretty disorienting for everyone, at first when you're first using Linux, is that everything that you have to do is done through text commands, right? And so there's no graphical GUI, and so you can't like point and click on stuff like you can, in Windows. Everything you have to do is through the command line, right? And so that's going to be really disorienting, I think, for a lot of people at first, because it's I think just we're just not used to it. Right? But once you get used to it, you kind of feel like really powerful, because you can operate things from your everything from the terminal, okay? All right, so before we move forward, I do want to go over some common Linux text commands, just so that you can do some basic operations in Linux. Okay? All right, and so I think in the document I've linked you an article, and so if you go to this article here, it shows you some very common Linux commands. So this one's really nice, right? But I think, but it also gives you, I think, 35 of them. And I think, you really only need to know like 7 or 8 of them out of those 35, right? And so for this part of today, and I think this is all that we'll do for the rest of today, we'll just learn how to basically navigate within the Linux system, okay? Right, and so to kind of, to kind of illustrate this, let me go ahead and pull up a folder, Windows Explorer here, because it's very analogous, okay? And so if you think about navigating through your files through like a Windows Explorer like this, but you think about doing this just with text commands instead, you're already going to be in great shape, okay? So actually, let me go ahead and go to let's just start here, right? Okay. Actually, let me go here. Actually, so let me go to my desktop. And so for now, I want you guys just to kind of sit and watch, and then you can kind of do it on yourself later, right? Because right now I'm going to, there we go. Okay. All right. So let me go ahead and clear this. All right. And so just so that you can kind of see things kind of happening in parallel, I've opened up one folder here with Windows Explorer. And so this is kind of our GUI representation. And then I opened up the same thing in Linux. I've gone to the same location, so you can kind of see things in parallel. So you can kind of see that, you know, we're doing the same things in both. Right? All right. And so let's do some basic commands. Right? All right. And so the first command that you should know in Linux is the pwd command. Okay. And so, oh, just very basically, you know, to enter a command in the Linux terminal, all you have to do is type in the command, right? And so in this case, I'm going to type in pwd, and then you can hit enter, okay? Right, and so by hitting enter, you send the command to the Linux terminal, and then it executes your command. It gives you, you know, whatever output that you may need, right? And so the first command that we're learning here is pwd, okay? And so, you know, I think this is the most commonly misconstrued you know, command in Linux, okay? Because most people, when they see pwd, they think of password, but pwd here doesn't stand for password. What it stands for instead is present working directory, okay? And so that's where the pwd stands for, right? And so when you enter pwd, what Linux will return to you is this thing right here, okay? Where this right here is called your path, okay? Right, so path, just like that, right? And so the path is basically, you know, how to locate this location is basically this location on your computer, you know, hard drive, right? And so the same thing in your Windows Explorer would be just the location of this folder, right? And so for this case, it's the desktop, and so the desktop is kind of the place where everyone stores just a bunch of you know, all the random stuff. All right, and so present working directory, pwd, that's a great way to kind of tell you where you are, okay? But, you know, for a lot of Linux distributions, you often don't need pwd, because if you notice here that, you know, in blue, what I have is basically the location here as well, okay? And so for a lot of Linux systems, they tell you what location you are in, basically from the command line right next to it, okay? But if you're not sure where you are, or you're working on a different system, you can use pwd to let you know where you are. Okay. All right. And so next command that we're going to use is ls. Okay. And so this is a lowercase l and a lowercase s. Okay. And so what this command does is that it lists all of the different files and folders within this folder. Okay. And so ls lists all of the files and folders within this directory. Okay. And so this is useful because, you know, because in Linux, you don't have this graphical interface here on the left, right? And so in order to find out what files that you actually have in this folder, you need to run this ls command, and that will tell you, okay? Because a lot of times, you know, you might go into this folder and your terminal might be blank like this, okay? And so in order to determine what files you have in here, you can just type ls, and that will show you, you know, which files that you have, okay? Right. And so I did this on purpose so that you can kind of see, you know, which files I have here, right? And so here on the left here, I have my Windows Explorer, and I'm on my desktop. And you can see here that I have all these files listed here, right? And so you can see here that I have the exact same files in here, right? And so some of these might be missing because some of these are shortcuts, like I have Twitch here for whatever strange reason, right? But you can see here, if we search for the file, let's say something that I don't mind showing here. And so let's look at ft01 Poisson, okay? Right? And so I can see that I have a file here called ft01 Poisson, right? And so if I look at my ls list from my Linux terminal, you can see here that I have an ft01 Poisson, okay? And you can see here that there's a, you know, there's a one-to-one correlation. So every file that I see here on my desktop, I can see here from ls as well, okay? All right, and so that's you know, a very basic operation for you to see, you know, which, you know, where or what files are in your current directory, okay? All right, so so any questions on this so far?
got confused after PWD. I understand everything what you explained, but can you re-explain PWD?
Yeah, sure. Yeah, so PWD is a way to kind of let you know where you currently are. And so remember, PWD stands for present working directory, right? Okay, and so it's kind of just a way to tell you where you are. And so the analogous thing for the Windows Explorer would be to kind of look at this bar right here, right? And so if you look at this bar, this tells you where you are. So if I move to a different folder, let's say I move to pictures, right? I have nothing embarrassing here, right? Okay, good. And so if I move to pictures, this bar right here tells you what folder that you're in. And so the pwd command is that exact thing where you ask Linux to tell you, where you are. Yeah. Okay. It's basically just your present location. So honestly, I actually don't use it much because most of my Linux distributions have this kind of thing right here, which tells you what your present working directory is already. And so typing out PWD is a little bit redundant because you have the location here already. But it's just a command to tell you where you are in your system. Yeah.
Thank you.
Mm-hmm. All right. And so, all we've done so far is just kind of observe things in Linux, right? Question. So PWD equals where you are here, and LS is what you can select next. Yes, perfect analogy. Yeah. Yeah, so PWD tells you exactly where you are, and LS tells you all of the files and all the folders that you can interact with within this directory. Yeah. Mm-hmm. Okay, and so let me go hit an LS just so we can see this one more time, right? And so the next command that I'm going to show you guys is called CD. Okay, and so CD here stands for change directory. Yeah. So Ronald, that's a very, very timely question. And so the next command here is how to actually change directories. Yeah. Okay. And so to change directories, and so let's say that we want to go into a different folder, right? And so let's say that we want to go into this folder called test files, right? And so if you want to do this on your Windows system, the way that you would enter it is you would just double click test files, and then you would enter into this folder, right? And so from the Linux, from the Linux side, from the terminal, you can't double click test files, right? And so you can click this all you want, but Linux will say, I have no idea what to do with this, right? And so in order to change directories or in order to go into that folder, the way that you need to do this is with a CD command, right? And so CD literally stands for change directory, right? Okay, and so you're going to do CD, okay, space, and then you're going to type the name of the folder that you want to go into, right? And so in this case, you're going to do, for my case, you're going to do CD test files, right? Right? And then you can see after I've done CD test files, you can see now my path has been updated. And so instead of just being on the desktop, now I'm on the best desktop / test files, okay? And so that tells you that you're in this folder, right? And so if you check this path right here against, this bar right here, right? And so this bar on the Windows Explorer that tells you where you are, okay? You can see here that we're on this PC desktop test files, right? And so you can see here our present working directory has been updated from, just the desktop to desktop / test files, right? And so that tells us that our move or change directory was successful. All right, question. So if you know where you're going, can you enter multiple locations in one command? Yes, actually, that's a great question. And so let me do that. All right, and so let me go back to the desktop. And let me go over that one more time too, right? Oops. All right, and so if you want to move up, if you want to go back to the previous directory, so you want to go up one level, right? And so on the Windows Explorer section, we have this kind of up arrow, and so this takes us one level up. And so if we want to say go back to the desktop, we can click on this up arrow to go back to the desktop, right? And so that always takes you one folder up. And so the equivalent for that in Linux is to do CD and then ... Okay, and so ... here is a special Linux location which tells you let's go one location up from here. Okay, and so you can see here after I hit CD ... I go from desktop test files back to desktop. Okay. All right, so on to Tyler's question. So let's say that you want to go into multiple folders or multiple nested folders at the same time, right? And so let's say that we want to go into test files, And then inside this test files folder, we want to go into user files, okay? And so we can do that. And so you can enter the full path here into CD, right? And so let's say that we want to go into CD test files, right? And then we want to, inside the test files folder, we want to go into user files, right? And so all you have to do for that is to enter the additional folder that you want to go into after a slash, right? And so you do CD test files, and then you do / user files, okay? And then you hit enter, and then you are inside this folder, okay? And in this case, this folder is empty, and so we don't have to worry about that, okay? But if you want to go into kind of multiple locations at once, then you can do that, okay? Or I should say multiple levels of files. Okay. So any questions on this so far?
I'm having trouble just like being able to access my desktop, I guess.
Yeah. So if you're following along, your desktop is actually in a special place, and so probably where you're in right now is you're probably in the Ubuntu home. Okay? And so mine is filled because I've used it before, but probably yours doesn't have anything like this. And so if you do pwd, yours might say /home/Jonathan or something like that.
Yeah, it does.
Yeah. So in order to access your desktop, it's actually in a special location because when you install Linux, it kind of creates almost like you can think of it as like a Linux partition, which your Windows system can't access. But you can access your Windows files from Linux. And so the way to access that is you're going to use a CD, okay? And you're going to go into a special folder called /mnt, right? And then here it's going to depend on what your drive system is called. But for me, I have 2 drives on my system. So I have a C drive, which is where my desktop is, and a D drive, okay? And so in order to check which drives you have, you can do CD /mnt / and then you can hit tab a couple times, right? And so so your tab in Linux is going to be your autocomplete. And so it's going to show you a list of which folders you can go into, right? And so I'm not sure which drive your desktop is in, but mine is in C. Yeah. So let me go in C, right? And then from here, you should be able to see your usual file structure. And so my desktop is under users, and then under Justin, and then under desktop. And so that should get you to your desktop. Yeah.
Okay. Thank you.
Yeah. So it's a little bit weird, but yeah, if you want to access your Windows files, you have to go to this weird MNT C users, that stuff like that. Yeah. All right. So let me go ahead and clear. Oh, if you want to clear your terminal, you can hit the command clear and then hit enter. So I'll be doing that just to kind of refresh the screen a bit. Okay. And so that's basic moving around in Linux, right? And so we have 3 commands so far. So we have pwd, so that tells you where you are. ls, that tells you, which files you have available to you. And you have cd, which is change directory, right? And so, that's the basics of, just knowing where you are, knowing where you can go and moving around in Linux, right? And so it's exactly the same thing as if you had your Windows Explorer here, and you could click around and move here, right? And so we just kind of did the Linux equivalent of that. Okay. All right. And so let's talk about autocomplete, because so autocomplete is kind of the best friend for Linux stuff. Question. So how do you open files and stuff? Yeah. So that's we might not get to that today, but you need to run things in a special program. And so like to open like a text file, normally when you double click a text file here in Windows, you can see here that Windows use the Notepad application to open the file. And so in Linux, the way that you have to do that is you have to use an application to access a file. And so probably for you guys, you guys just have kind of a fresh Linux distribution, so you don't have that many applications. But if I wanted to open up a text file, a popular one that I like to use is called gedit. And so you guys don't have this installed yet, so you can't use this, right? And so if you do gedit, let's say, this file right here, and this will open up a text editor for me to do. But you can't use this yet because you don't have gedit installed, but we'll install gedit next time. But basically, in order to interact with files and to open them, you have to launch it with the program. Yeah. Mm-hmm. Okay. So before we do that, let's talk about autocomplete, right? And so autocomplete is your best friend, right? because as you can imagine, if you have to type out, the full names of files and full names of folders, it gets very cumbersome, right? And so let me go ahead and clear this, right? And so let's say I wanted to CD into this folder right here called test simulation converted results, right? And so in order to CD into this, I would type CD test simulation converted results, right? And so, that didn't take that long, but you can imagine, if you have longer file names, it becomes a chore, right? And so one feature that the Linux shell has for you is called autocomplete, right? And so the way it works is that if you start typing out the name of a file or folder, right? Okay. And so in this case, let me just type out test_s, okay? And if there's no other file or folder that starts with that same thing in your current directory, if you hit tab on your keyboard, then Linux will autocomplete that for you, right? And so instead of having to type out test simulation converted results, what you can just do instead is do cd test s tab, and then it's going to complete it for you, right? And then that's way faster to do, than typing out the whole thing, right? Right, and so same thing here. So let's say that, I have this really long name called all results averages from CM to MMHG L per min.txt, right? And so that's a big ass name that I don't want to type out because I don't want to do gedit, all results averages from all yada, 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 okay? And so instead what I like to do is autocomplete. And so, good use of autocomplete is really useful for, for good Linux stuff. Yeah, I can go back. How do you go back folder? You do cd ... Yeah. Yep. Right. And so the danger with using autocomplete, or not really danger, I guess the annoying thing is that if you have multiple files that start with the same thing, okay? And so let's say I want to do cd test, right? If I hit tab here, right? If I hit tab, then, Linux will say that, you have multiple folders here that start with test, right? And so you can go to test ANSYS 2021 files, you can go to test files, or you can go to test simulation converted results, right? And so you hit tab multiple times, it'll tell you, which files or folders that are eligible for you to move into. Right? And so in this case, I want to go into test simulation converted results. And so I just have to finish typing that and hit tab. And then we can go into there. Okay. All right. Okay. All right. And so that's tab autocomplete. And so getting good at tab autocomplete is an essential skill for using Linux. Okay, because having to type out stuff all the time is is a big pain. Okay. So any final questions before we wrap up for today? Okay. All right. Okay. So Monday, we'll really dive into the Linux stuff. We'll really dive into the OpenFOAM stuff. This kind of just barely scratches the surface, but we'll learn more Linux commands on Monday. We'll get more practice doing it, and then we'll go from there. Right. So hope everyone has a good weekend. Keep working on your projects. Let me know how you're doing. And I'll see you guys next week.
Can I pick your brain a little bit more?
Oh yeah, sure. What's up?
So I got it to the point where I got it to the users, right? And then on mine it says all user default user public desktop, and then my name. So when I choose my name, it says this is a directory, and that's it. Yeah,
so you have to CD into that directory. So you have to CD into your Jonathan directory, right? Because you want to go into there, because that's that's kind of the same thing as going to your going into that folder. Yeah.
So it'd be CD and then my name.
Yeah. Mm-hmm.
No / after CD, right?
No.
Okay. CD.
You have to do CD space ... And so it's not CD ... It's CD space ...
And it's case sensitive too, right?
Yeah. Mm-hmm. Or where are you right now? So when you type PWD, where does it say that you are?
Let me check. MNT.
Oh, MNT. Okay. Oh, okay. So you're not into and so if you're on MNT, let me go to MNT for you too. Okay. All right. And so you have to enter basically each folder individually here. And so if you type ls, right? And so right now these are the available folders that you can go into, right? And so for me, I have 2 drives, which is C and D, right? And so if I want to go into my C drive, I have to do CDC, right?
CD. Okay.
Right, and hit enter, right? So now you're in your C drive and you hit ls, right? Okay. And then from here, I know that I have to go to, where is it? I think users, right? Where's users? Oh, right here. Yeah. So if CD users, right? Because I have this users folder here, right? Oops. Okay.
Oh, this makes sense now.
And then now that I'm in users, I can do ls. And you can see that I want to go to Justin, right?
Okay.
I don't know what's up with my colors, right? But and do CD Justin, right? And then ls, and then from here I can go to my desktop. And so I have a lot of folders here. And so I can go to CD desktop.
Oh,
and then here's the desktop. Yeah, so you have to CD basically kind of one level at a time. Yeah.
And it's case sensitive, right?
Correct, yes. Mm-hmm.
And then ls.
Yep.
Nice. Okay, this is pretty cool.
Yep. Yeah. So once you get used to it, and once you really start getting fast, it is really cool. Yeah.
So okay, so I'm on my desktop now, right?
Mm-hmm.
And so now, for example, if I want to go into, let's say, one of my files, I just CD space type it and then / and then it should go into that file.
So you can only do folders at this point, and so we can't open files yet.
Yeah. Sorry, that's what I meant. File,
yeah.
like file folder. Yeah.
Yeah. So if you want to go into a folder, you can go to CD into test files, right? For my case, it's test files, and then you can go into that folder.
Okay. Mm-hmm. So if I did, and what was that you were saying? Sorry, I was trying to like multitask. What was that you were saying? Like if when you have a long file name, you said put gedit.
Oh no, so you can tab, and so if instead of typing out the full name for stuff, you can use tab to autocomplete. And so let's say I want to go into the test files folder, and so instead of typing out full test _ files, what I can do is I can do test F, because there's no other file or folder in here that starts with test F, and I hit tab on my keyboard, and then when you hit tab, it autocompletes to that. Mm-hmm.
Okay, but if there's another one that had an F, it wouldn't do it.
Exactly, right. And so if I do test _ as you can see, I have several folders here that are test, right? And so if I try to do tab, it can't autocomplete, but it will tell me, which folders start with test that I can go into.
And then from there, okay, I see what you mean. And then you have to type it out.
Yep. Mm-hmm.
Nice. All right, cool. Thank you.
Yep. Mm-hmm. What does Linux have against GUIs? Nothing really. It's just, I think, because a lot of the earliest systems were kind of built on this, and that was kind of before graphics cards became really a thing. And actually, a lot of, supercomputers. So if you want to run like, I know you guys are using the website for 442, but if you wanted to access the gateway website is something that that was developed to put on top of a cluster. And so normally, if you want to access a cluster, it's you have to use a text terminal like this, because if you're building like a system with like thousands and thousands of processors, it's kind of a waste of money to buy like a GPU for each and every single one of them. And so the only thing that you really need is just a computing unit, and then you can have more space for like RAM and other stuff like that. And back in the old days too, like when graphics cards weren't as reliable as before, like if something went wrong on your computer, like you would probably have to debug it with a terminal like this. And so it was kind of like a fail safe in case the GUI wasn't working. Mm-hmm. Right now, it seems really weird. I agree, but you know, once you start you know, running programs, and especially for developing code, you know, Linux is going to be your system for that. Yeah, but for just you know, everyday just file management, you know, I definitely preferred, you know, the GUI and be able to click stuff, but for development and for you know, and for debugging stuff, then Linux, that's where Linux really starts to shine. I see. Yeah, I guess that's not surprising, because probably a lot of yeah, probably a lot of codes and a lot of like servers and stuff, a lot of them probably run Linux. And so if you have some experience with Linux, then you know, it's going to put you ahead in those companies. Yeah.
Professor, in the same way how you could see move forward, what command do you use to move backward?
Oh, can you say that again? Sorry.
In the same way how you use CD to move into a folder, how do you move out of a folder? How do you go back?
Yeah. So to go out of a folder, you have to use, you can use the CD command again, but you have to do CD space ... Oops. And so let me put it in the chat. And so if you run this command, so CD space ... then it takes you out of that folder.
Oh, I see.
Yeah.
Thank you.
Yep. Mm-hmm.